So this class is about the Langevin equation, and it assumes some knowledge about Brownian motion. So I would like to give the context of this equation. So suppose you're interested in following a trajectory. So this is, for example, the red trajectory here for any of an ion, let's say, occurring inside the cytoplasm of a cell or inside the solution. So we would like to characterize the motion and thus describe trajectory so that they can be, for example, generated on a computer, or they can be used for analytical purposes. So for this, the classical Langevin equation, and I will come back to this, is an equation that for the acceleration, the friction force, so it connects this quantity to a possible interaction force and to some random noise forces modeled as Brownian. So for example, the potential well can be of an electrostatic type. And so this provides a description at a single particle level. So I will explain later on what is the meaning here of the coefficient gamma and the origin of this term, which is square root epsilon multiplied by gamma. So once again, x is the position of a particle at time t. For example, in dimension 2 or dimension 3, it will have 3 components. And in this Cartesian component, this equation here can be written. And this is a stochastic equation, so it's not deterministic, so it cannot be solved in a deterministic way using, for example, the classical Cauchy theory. So it has to be understood in a probabilistic manner, so that each trajectory is stochastic. So that's why I wanted to be sure that anybody who's going to read this has some knowledge about Brownian motion. So again, we are trying to see this motion of particles. So here they are going through a channel, which is usually, this also can be modeled using the Langevin equation. And also ions that are in the bulk can also be modeled by this equation, but of course this is quite challenging, because if you think about a positive charge, it can interact with negative charges here and the chloride, although we really do not understand how long is such interaction and how long it takes, since ions are quite moving, we can say, freely in the cytoplasm. So there is also an interesting concept, which is the limit of large friction. So when gamma is large, and so we will discuss this limit, is that this stochastic equation, which is a second order stochastic equation, can be replaced by this first order equation, in the sense that the probability density function for the first one converges in probability, converges in distribution term to the probability distribution for the one where there is no second derivative. And thus, this is usually the model for the description of a stochastic particle in the regime of gamma large. But as we are going to discuss a bit, so this is there is some limit where this cannot be applied. For example, if the time at which we are looking for the trajectory is small enough or comparable to 1 over gamma, it may lead to some difficulties. And also for the motion of an ion inside the channel, it has been shown that the Smoluchowski limit is not enough. Another things that we are losing by using this approximation is that when we have, for example, if we approximate a chemical reaction by a site here, and we say that a particle, when it enters here, it's trapped, then when you have unbinding of this particle inside this potential well, usually the particle has to be placed, for example, if you think about a simulation, not at the boundary, because this means that the particle is absorbed again, but at some distance away. Well, if you use a Langevin equation, if you release the particle with a velocity, then the particle will escape and doesn't need to be released manually at a certain distance away. So classical books for this are the book of Schuss 2010-2009, Theory and Application of Stochastic Processes, and also the one of 1980 about stochastic equation, and also the classical book of von Kampen or Risken. So yeah, so this Smoluchowski limit is a general model of a stochastic equation where the velocity x dot is results from a drift term which can model interaction or simply a flow, and an effective diffusion coefficient d of x. So we can write it in this general form, and the difficulty usually in modern analysis of single particle trajectory coming from live cell imaging is to reconstruct the drift and the diffusion coefficient, because once they are known, all trajectory can be simulated, and of course the prediction can be made about large statistics, for example, the time it takes for a particle when it started at position X to move to position Y. So assuming that, supposing all of these beans here, we know in each bean, we know the coefficient B of X and D of X, then any simulations, or it's also possible to solve stochastic partial differential equation in empirical domains. But basically, this is what is needed to get statistics from empirical data. And D of X is usually connected to the amount of crowdedness. That is, if you have if you have obstacles, this is more or less the density. D of X can be connected to the density of obstacles that a particle has to go if it wants to continue traveling. But one thing is for sure, this is not connected to any binding which is in the drift term. So I would like now to start with the presentation of the Langevin equation. And this is a derivation that was, it's due to the physicist Chandrasekhar, 1945. So suppose you have a particle embedded in a space where it can feel collisions of a particle. That is, you have any particle that are coming and generate a collision with this particle. So that's the mean number of collisions. So we will write it this way: the mean number of collision is 0. So F is connected to the forces, that is forces on the particle, let's call it P, on the particle P that is free to move, and let's say can be characterized by its position x of t and its velocity at time t, which is v of t. So then, so we assume that all forces are generated isotropically. There is no preferential directions for this. And so the second assumption we are going to make is that there is a drag force, and this drag force is going to be proportional, so by a coefficient gamma, to the velocity v. And so The first equation to be written to describe the motion of the trajectory is the classical Newton's equation, the Newton equation of motion. So Newton equation of motion, which says that the force, the acceleration dv dt, should be proportional to the force. So this is minus gamma, the friction, v, plus the collision force that the particle experience. And here for this derivation, we'll neglect here at this stage, but it could be done with all the other forces. So we will neglect all the other interaction. We'll neglect all other interactions. So, which means that, for example, no electrostatic forces. Electrostatic forces. So, in that case, we would like to, so F here is going to be, so the force F is all the forces that are due to the collision. So in principle, this is a random force. We don't know when it happens. Particles are arriving at a random time and collide. So to describe this random force, I would like to remind you the classical result from gas theory, where if we have a particle moving in the gas theory, Boltzmann has already described the distribution of the probability for the velocity. So let me remind you that in the gas equation, so in gas theory, and this is how we are going to consider such a particle, the probability that the velocity v of t belongs, let's say, to a set A, condition that, let's say, v at time 0 equals v0, this is simply the integral of the probability distribution function to switch from v0 to v during time t dv. And we know that, so two things about this probability distribution function. Pt of v and v0, condition on v0, when t goes to 0, they should converge to a delta Dirac at v0. It is, of course, normalized to 1 by definition. So p of t v0 integrated to all the space of velocity. So here this is, let's say, in the entire space, the entire space of velocity is just R3. So this is simply, or any space you're interested in, which is, for example, omega, this is equals to 1. And so we know that what the Boltzmann distribution is telling us is that the limit when t is very large of pt of v and v0, this, as t goes to infinity, it converges to the steady state, which can be written as m divided by 2 pi. So m is the mass, kb is the Boltzmann constant, T is the absolute temperature. So if we're in dimension 3, this is 3/2, exponential of minus the energy, that's the kinetic energy, mv squared, so this means the norm of v, divided by kbt. And this is independent, so this is just a remark, this is independent of the initial velocity of v0. and this is in dimension 3. So to get insight into the force F, we are not going to, so we're going to use this in a second. So now we are going to integrate the equation that we have discussed. So we have V dot plus gamma V equals the force, which means that we can directly integrate this equation using the classical calculus, which says that V exponential gamma t, if we differentiate with respect to t, this is equal to force, which depends also on t, multiply by exponential gamma t. So now this is, after integrating with time, we obtain V of t exponential gamma t, so, or minus V0 exponential minus gamma t equals, and so this is the integral from 0 to t of f of s multiplied by exponential of, so this is minus gamma of t minus s, gamma of t minus s ds. So gamma of t minus s ds. Okay, so now if we go to the limit gamma t large, so for this, clearly this term here, the term v0 as t goes to infinity, when t goes to infinity, this term here converges to 0. So all of this goes to 0. So now what we need to study is this second term, which is this one. So we are going to discuss this now. So for this, let's rewrite the integral. So we need now to discuss the integral. So let's use the classical. So we need to integrate from 0 to t of a function f of s exponential minus gamma of t minus s ds. And so for this, we're going to use the same trick that we have used to describe the stochastic integral. We are going to divide the integral from the interval from 0 to t in many small pieces. So we call this tk and tk plus 1, so that we can approximate this integral as the sum, which is the sum for k of f of k delta t. So let's suppose all of this interval is of the same length, delta t. So this is tk plus 1 minus tk. And so this is multiplied by exponential gamma of tk minus k, so s is now plus k delta t and multiply by gamma. So the notation here, I will take the notation d omega k is equal by definition of f of k delta t multiply, so in here I forgot to multiply by delta t. Delta t is the step of the integration, so multiply by delta t. So by definition of the property of f, since we said that the forces are isotropic, the expectation of the force F. So now we're trying to find what are the stochastic property of F. So by definition, this is going to be d omega k is going to be equal to 0. All collision can occur in all directions. And now since the forces applied to this particle is due to independent, identically distributed forces occurring in all directions, basically by the law of large number, the sum of this has the properties converges to a process which is Gaussian. And thus, the expectation for d omega k squared is going to be equal to a term that will going to be 2q, and q is an unknown, multiplied by delta t. So q is going to be here the unknown parameter. So this is unknown to be computed. Okay, so let me remind you that this is exactly the same procedure that we have studied when we looked at the space of non-anticipating functions. So as a consequence of this, if we just look at the sum in this the sum above, clearly the expectation of the sum is 0. So of exponential of gamma s f of s ds, this by definition equals to 0. And so the second thing we would like to calculate to characterize this coefficient gamma, this coefficient q, is to look at the expectation. So this says that basically the expectation of the velocity is 0. That is, the particle has equal chance to move on the right or on the left. So, however, a characterization of the motion will be given by the velocity squared. So we would like now to calculate the expectation of this, and as t goes to infinity, this we have seen converges to the expectation of v, and we know that by Boltzmann this is characterized by the Boltzmann distribution, which is simply the integral over the space of v squared. So this is the velocity squared multiplied by the distribution, which is m divided by 2 pi kbt so we have to integrate. So m 2 pi kbt to the power 3/2 to the power 3/2 multiplied by the Gaussian exponential of minus m v squared divided by 2 kb, so divided by 2 kbt, so k Boltzmann multiplied by the temperature T. And here we have 2 kBT. And this is now multiplied by the volume element dV. So this is a classical integral. dV here is the volume, so dV here, by definition, this is the volume in the space of velocity, which is equal to 4 pi. So this is 4 pi multiplied by v squared, so 4 pi v squared, and then multiplied by dV. So this is the volume element. So this integral is well known, and in dimension 3 it is here equal to so this identity can be computed by integrating by parts, and this is equal to 3 multiplied by kb multiplied by temperature divided by the mass m. Divided by m. Alright, so now what I propose to do is to calculate in a similar manner we have calculated v of t. Now we are going to calculate v square of t. So for this we are going to use the equation that we have just written for v. So v square of t is by definition equal to v0 exponential minus gamma t plus the sum of exponential minus gamma t exponential k delta t gamma d omega k. And now we have to use this calculated square. And so again, this is not very hard to calculate. This is v0 square exponential minus 2 gamma t. So clearly as t goes to infinity, this goes to 0. There is also a term, a second term, which is d2 v0 exponential minus gamma t, the sum of k exponential k delta t gamma d omega k. So the expectation of all of this, and also as t goes, the expectation of this is equals to 0. Expectation of this term is equal to 0. And then we are left with plus exponential of 2 gamma t. So this is v of t. Here this is one of the components for v of t. So this is, for example, the x component or the y component. So it's minus 2 gamma, and then we have the sum of exponential k delta t multiplied by gamma d omega k, and everything is squared. So the limit, now we're interested in the limit of the expectation of v square of t. This is to connect always the Boltzmann results of the limit of this as t goes to infinity. So this is going to be by definition, so we should really write it without the limit, but just like this, expectation of this as t goes to infinity. So let me just remove this part here. So this is going to be of the order of exponential minus 2 gamma t. And now what we need is to, and we need to calculate the expectation of the sum of exponential k delta t gamma d omega k, and everything is squared. So this sum can be evaluated in the same manner that we have evaluated the sum when we manipulated the Brownian motion. So this is exactly, I mean, all the terms, so this can be written as the double sum over k and q when, and we should write it exponential k delta t multiplied by gamma plus q delta t multiplied by gamma, and then we are left with d omega k and d omega q. And the expectation of all of this term here is going to give us 0 except for k equals q. So we are going to be left with exponential of minus 2 gamma t. And then, so we have to sum over k of exponential 2k delta t gamma. And then the term we are left with is simply going to be the so d omega k, d omega q, by definition, this is going to be delta t. And I think that's it. So we are left with this, and we have to sum this over the so this is simply, now we can recognize that this is simply the Riemann integral. So this is exponential minus 2 gamma t of integral from 0 to t of exponential of 2s gamma ds. And wait, and we have to, well, yeah, we have forgotten that there is here a factor 2q, where q is due to the, by definition, of the variance of the omega. So here we are left with 2q. Q is different than the q variable where we sum. Let's call it, this is q1 here, q1 and q1. While we have said before that 2q by definition was equal to the expectation of d omega squared, which will write it this way. So finally, this calculation, now we are just left with a classic integral to calculate, which is expectation of minus 2 gamma t multiply by, so this is will give us exponential of 2s gamma divided by 2 gamma and minus 1 multiply by 2q. So minus 1 multiply by 2q. And in the limit t large, this is simply equals to q divided by gamma multiplied by 1 multiplied by 1 minus so multiply by 1 minus exponential of minus 2 gamma t minus 2 gamma t. And so when t goes to infinity, it converges simply to q divided by gamma. And so finally, what we have found here is that using the Boltzmann identity for the limit of the velocity, so we have studied the expectation of vt squared as t goes to infinity, which was converging to this quantity. So by comparing the two sums, we have 3 k Boltzmann t divided by m, which is equal to, now remember we did this calculation, the previous calculation for v, as if it was dimension 1. So now we can do that in the 3 dimension, and so this is equal to 3q divided by gamma. So then we are left with the following identity, that q equals k Boltzmann multiplied by gamma temperature divided by m. So now we can rewrite the Langevin equation, which is m v dot plus gamma v equals f, where by definition f, which was fk delta t equals, so multiplied by delta t, which was by definition d omega k, which we can rewrite using the normalization of a Brownian motion, which is of variance 1, d omega k tilde, multiplied by square root of 2q. Right? So when now, by definition, the expectation of d omega tilde of q squared, this is Brownian motion, is equal to simply delta t. So what we have by definition, we can write formally of f of k delta t equals d omega k tilde square root of 2q divided by delta t. And so this can be written, so now we just replace by the different parameters. So this is we go now in the limit of delta t goes to 0, so the infinitesimal version of this is, so generically omega k is a discretization of omega, so this is simply omega dot, where we write by definition omega dot is formally the limit as delta t goes to 0 of this ratio of d omega tilde divided by delta t, where d omega tilde, let's say at time t, is simply equal to omega of t plus delta t plus delta t minus omega of t. All right, and so what we have seen now is that this is simply equal to square root of 2 gamma epsilon divided, so here there is no m in this equation. This was the equation we have written. So divided here by m, omega dot, where by definition we say that epsilon, the energy, is equal to k Boltzmann, so kBt. This is kb multiplied by the temperature. So this is now the formal derivation of this Langevin equation, which assumes isotropic forces, the fact that the drag is proportional to gamma v. It's not necessarily the case all the time. So there are other assumptions which leads to different equation. For example, so now we just are discussing one remark. So what happened when we have not necessarily this proportionality? So for example, in a crystal, it has been shown that the correct description of a particle is x dot dot plus gamma integral of from 0 to t of phi of s x dot s multiplied by ds plus forces, so I write it formally here, v prime of x, the derivative of potential, equal psi of t. But this requires specific condition between, as we have seen here before, there's specific condition between the noise, the amplitude of the noise, and the function phi. And this is called the classical fluctuation dissipation relation, which says that the expectation, or the variance really, or the correlation of the noise between time t and time ti and tj are connected to gamma k Boltzmann multiplied by temperature phi of the absolute difference ti minus tj for all I and j. Alright, so this is an expression of a theorem that I'm not going to enter into details. This is called the general fluctuation dissipation theorem. Fluctuation dissipation theorem, which assumes homogeneity of the space. For example, if the particle is near a wall, then there will be, of course, this assumption is broken, because if you think about a particle close to a wall, it doesn't receive uniform distribution of collisions, only on one side. So for example, in a crystal, so this is the case where it can be broken, and also this equation is not exactly, cannot be used like this if we want to extract the diffusion or force property inside the membrane, because inside the membrane you have a lot of obstacles that affect the diffusion. There is no here freely diffusion, because it is diffusion in a crowded medium. So the diffusion, the real diffusion, and the diffusion measured are usually very different, especially when also there is a sampling due to the instrumentation. So this will be discussed in the class about analyzing single particle trajectories. So a typical example of the function phi is phi of t for a crystal, which was shown empirically to be working with sine omega t divided by omega t. So basically when omega is close to 0, then it's like 1. So we have used before, and so this creates, of course, correlation. So we have used the case where f is delta correlated. There is also an important case where phi of t is alpha exponential minus omega t. This is to look at a version of the colored noise. So for example, for colored noise, this is a Brownian, this is derived from Brownian motion. So the colored noise is u of t, where u is basically given by the equation u dot plus alpha u equals the Brownian motion, for example, the coefficient alpha w dot, or let's say, I'm sorry, let's call it capital A. So as alpha is playing a role of a filter. So when alpha is 0, this is simply Brownian, but when alpha is large, this u is going to filter. This is a low-pass filter. U is a low-pass filter. That is, it only gets the noise, the frequency, the low frequency. All right, you get rid in U of the fast frequency of W. And this is an important noise which is used, for example, in signal processing. So now we can continue the equation by integrating the equation a second time. So now I'm done with the remarks. So we had here several. So now I would like to continue with the further integration of the equation. So further integration. So what does it mean? It means that we have v dot plus gamma v equals, so it was the force, which we have seen can be written 2 epsilon gamma divided by m multiplied by w dot. So we integrated once v, and this is how we found this coefficient. Now we can integrate one more time to get x. So by definition, x dot equals v. So now we have to integrate twice. So x of t equals x of 0 plus the velocity at time 0, which is going to be 1 minus exponential gamma t divided by gamma, equals, now we have to integrate twice the equation. So this is integration of exponential of gamma of u minus s f of u du ds. So we integrate u from 0 to s and s from 0 to t. So I will leave this as an exercise. You just have to switch the integrals, and this is equals to integration from 0 to t of 1 minus exponential of gamma u minus t divided by gamma multiplied by f of u du. Right, so I'm sorry, this is here, this is x of t minus this, which is equal to this. So now we can look at the property of this difference of x of t minus these initial conditions. And so if we call this a function j of u, so I will leave this now as an exercise, but the expectation of the integral from 0 to t of g of u multiplied by f of u du, this is equals to 0. That is, it comes from the property that f has basically this property. So the difference x of t minus x0 plus v0 1 minus exponential gamma t, basically this is, for those who are familiar with Brownian motion, this is going to be a Brownian motion as the integral of a Brownian motion. I mean, of a function j of u, and this j of u is a deterministic function, so it can be fully characterized if we know the variance. So for this we need to calculate the expectation of the integral from 0 to t of, so the same thing with j of u, f of u du, and then we want everything squared. So this can be done again, either you know the stochastic calculus or you decompose this integral as a sum. So let me just write it for those who are not necessarily familiar. So this is the sum of k and q of j of k delta t, so k delta t multiplied by f of k delta t, and now we have the same for multiply by j of q delta t multiply by f of q delta t. And we have to sum, so by definition, and this we have to multiply everything by, no, I think that's it. So what we said last time is that there was, in addition, yeah, we have to multiply everything here by delta t twice, because this is twice. But we have defined previously f, so let me use a different color. So we define this quantity here as omega q. So we are left with basically everything is going to be to cancel when we are going to take the expectation of all of this. So when we'll take the expectation, everything will cancel except the term for k equals q. And we will be simply left with, so now I'm going, I will skip some elementary steps. This is now the integral from 0 to t of the function j square of s ds multiplied by 2q ds. So this is 2q multiplied by ds. And now this can be calculated explicitly because the function j is known. So this is simply 2q. So let's write it this way. This is 2 2q so let me erase this so the final result for this can be written as 2q, the integral, so 2 q, the integral from 0 to t of 1 minus 1 minus gamma, so exponential of gamma u minus t minus u minus t divided by everything here divided by gamma, and we have to integrate du. So this, by definition, will give us the variance. So let's call it sigma square of t. Now, if we write the entire integral, this is 2q divided by gamma square. So again, I'm just giving you the results. This is very easy by a direct calculation. This is t minus 2 exponential minus gamma t, exponential gamma t minus 1 divided by gamma, plus exponentials minus 2 gamma t. So here we're missing a factor 2, exponential of 2 gamma t minus 1 divided by 2 gamma. All right, where now by definition q is gamma K Boltzmann, so gamma K Boltzmann temperature divided by m. All right, so this term is just simply equals to 2 epsilon divided by gamma m multiplied by the same quantity here, which I'm not going to rewrite. So this allows us ultimately to characterize the joint probability. For example, we can use what we have calculated before to calculate the joint probability of x of t being located at x, and let's say the velocity equals v, condition, let's say, on x0 that initially the position is x0, v0. We can also estimate or calculate the marginals, or simply simply here the probability that x of t equals, so for example, if instead of x we use the probability that it is equal to x minus x0 minus v0 of 1 minus exponential minus gamma t divided by gamma, we already said that this quantity, so condition on the initial position, so suppose we'll just look at this quantity. By definition, this is a Gaussian of variance sigma, so this is simply 2 pi sigma t to the power, so if we are in dimension 1, this is 1/2. In higher dimension, we'll have to use all of this quantity for all coordinates. So let me just write it in dimension 1. Exponential of x squared divided by, so this is simply 2 sigma t. This is the classical Gaussian expression in dimension 1. So why this is, so now we can replace sigma by what it is. And so this is interesting because this, so sigma here depends on gamma. And so what we can say is when gamma is large, for example, this probability distribution function, P, becomes the probability that x of t, let's say, equals to x minus x0. So let's, gamma goes to infinity. This is simply equals to, so now we can use in the expression, in this expression for sigma, which is given here, what happened for gamma large. So for gamma large, the first term behave like 2 epsilon divided by gamma m, while all the other term here will go simply to 0, and they go to 0, so I insist not uniformly, because when t equals to 0, gamma cannot be compensated. So for t larger than, let's say, t1, a certain time, then we have that this is equivalent really to a Gaussian with the classical property, which is 1 divided by 2 pi multiplied by 2 kt. So this is 2 pi multiplied by 2 kb t divided by m gamma. So this is m gamma multiplied by the time, because it becomes nonlinear in time, to the power 1/2. And then it's multiplied by the exponential of minus the, so I could have changed here x minus x0, so let me just write it here, x squared divided by the same quantity that we have seen. This is 4 kt divided by m gamma multiplied here by the time, which is simply the Gaussian. So this said that when gamma is large, the Smoluchowski, the probability distribution of the Smoluchowski of the Langevin equation is the Brownian motion, which is called the Smoluchowski limit. And let me remind you that we need here that the time is larger than something, and this something plays sometimes a key role. So all right, so then we will say this. We will say that when gamma is large, so let me just summarize this summary, that when gamma is large and t has to be larger than some quantity, so it's not uniform, the result is not uniform for all time, is that when we have the Langevin equation x dot dot plus gamma x dot equals 2 gamma epsilon m w dot. So this is also true, but I'm not going to show it here. For this, we will need to do asymptotics on the Fokker-Planck equation. But what I'm saying is also true when we add here a potential v prime of x, that this equation, this stochastic equation, converges to the Smoluchowski limit, which is x dot gamma x dot plus v prime of x equals 2 gamma epsilon divided by m w dot. So this stochastic equation converges to that one in a sense in law, and thus for any simulations or any analysis in an overdamped medium where this property is true, when as gamma goes to infinity, we can use this Smoluchowski limit. So this is the Smoluchowski limit of the Langevin equation So I think this is important because this tells us what kind of equation we can use to describe trajectories in a medium such as a liquid or the cytoplasm of a cell. Okay, I'm going to stop here. there are many applications for this, which I'll present for the next class, especially, for example, how to model the current in probabilistic term, the current inside ionic channels. So before, let me just give you some references. So the first analysis, an analysis, possible analysis for the Smoluchowski limit is done in this in the book of Shoes, page 7 for the Langevin equation, and 259 for the Smoluchowski limit, which uses the asymptotics in gamma of the Langevin of the Fokker-Planck equation. And the first term that appears is simply the Fokker-Planck equation for the one order process. And there are other interesting references. So this is also the first book, 1980, and the reference of Carling Taylor.